Alright, this is Mr. Gillum. Today we're going to continue on with similar triangles, and we're going to learn a couple new theorems, and they're pretty straightforward today. But one of the things I do need to remind you about is what an altitude is. And an altitude is if you have a vertex and you connect it to its opposite side and it makes a 90-degree angle, then that is considered an altitude. Alright, so in this case, these two triangles, AD is an altitude and FJ is an altitude because it connects the vertex to its opposite side and it makes a 90-degree angle. It doesn't guarantee anything about these side lengths here. It just guarantees that it's a 90-degree angle from the vertex to its opposite side. Alright, there's a relationship between the altitudes. Now, previously we could just compare, okay, AC to FH would be like AB to FG, and so on, things like that. We know these relationships and we can set up these proportions, but now, given that the triangles are similar, so they have to be similar first. It doesn't go for any altitude. They have to be similar using angle, angle, side, side, whatever it is. We have to guarantee that they're similar first, but then if they are similar, we know that their altitudes make a ratio that is also equal to the ratio of their side lengths. Okay, and so this is a theorem you actually have to kind of write out if we're doing a proof. And so instead of writing all of these words up here, there's a little abbreviation that I'd like you to use. Similar triangles have corresponding altitudes proportional to corresponding sides. So if you're setting up a proportion in your equation or in your proof, probably that is using the altitudes, this is how you'll have to abbreviate it. It's a lot of words, I know. That's as short as we can make it. So let's just take a look here. So that just guarantees that if I compare the altitudes now, so AD compared to FJ is always equal to AB to FG, or it would be equal to AC to FH, or you could even say CB to HG. Okay, so if the triangles are similar, the altitude follows the same scale factor as your similarity statement. Okay, so like I said, it's pretty straightforward today. Before you can use this theorem about the altitudes, what you have to know is that they are similar triangles. So if I look at these triangles here, and I'm trying to use this theorem, KLM and YXZ, we need to make sure that they're similar. So it looks to me like we have one angle here and another angle here. So that tells me through angle, angle that for sure that these are actually similar. So we can go ahead and use our theorem. And like I said, the theorem is kind of hard to remember because there's a lot of words. It's similar triangles have corresponding altitudes proportional to corresponding sides. So the more we say that, the more familiar we're going to be with it. Similar triangles have corresponding altitudes proportional to corresponding sides. All right. So that means that in this case, my unknown is the x value. Now, we might be able to finagle away to find the x value using Pythagorean theorem if there is more information, something like that, because we are dealing with right triangles. But in this case, they're not giving us enough information to find all that stuff using anything else besides this theorem, which is similar triangles have corresponding altitudes proportional to corresponding sides. So what we need to do is we need to decide which way we're going, either from the big triangle to the small triangle or small to big. And we need to say, okay, well, this theorem guarantees that these altitudes, the ratio of the altitudes is the same as the ratio of the corresponding sides. So that's what I'm looking at right there. I'm going to say that 16 to x is equal to 20 to 15. All right. Now, I just want to address this issue because I've noticed on some of the homework assignments that people are making this mistake. Yes, I know that they're guaranteed to be, they're similar because angle guarantees they're similar. But some people have been comparing 16 to 20 and x to 15 like this. And there's issues with this because we always need to compare one triangle to the next triangle, one triangle to the next triangle. We're talking about similarity. We're not comparing the ratios of the triangle itself to another triangle that is indifferent. We're comparing a side length or an altitude to the side length or altitude of another triangle. Okay, so do not use the same numbers in the same ratio from the same triangle. We don't use 16 and 20 in the same ratio. We use the 16 on one side of the equal sign. We use the 20 on the other side of the equal sign. Okay? Do not use the same numbers in the same ratio. Okay? I just want to illustrate that for you real quick. I could have this triangle down here, like so, and say that this is 2, this is 4, and the second triangle here that is, let's just say, 6 and 12, and I could compare, okay, yes, 2 to 4 is equal to 6 to 12. This is an incorrect statement. Incorrect, because the same 6 and 12 could be this way, and I would get the same proportion, and obviously these two triangles are not similar even though these are. So if you're using the same numbers and the same ratio over here like so, or like 16 and 20, they're on the same triangle, it's going to cause issues because there's no guarantee there when we're comparing two triangles if we're not actually comparing the triangles. Okay, so make sure that when you set up your proportion, you're using first triangle, second triangle, first triangle, second triangle. All right, and you keep it in that same exact order. You can't use the same numbers from the same triangle. So that can be kind of confusing. I just wanted to clear that up. This is all just kind of gibberish from the problem. Now we can get back to what we were doing. Just make sure you're setting up your proportions properly. The 20 compares to the 15, the 16 compares to the x. All right, now it's just a matter of solving. So let's take a look here. 16 times 15, let's see, I think that's 240. Equals 20x, and I think that it's 240 because I know 15 squared is 15 times 15. That's 225 plus another 15 on top would be 240. And then I would just divide both sides by 20. So x equals, okay, there's 5 20s and 100, so 5, 10, and 2 more, 12. All right, so in this case, I would say that this altitude here, x equals 12. All right, pretty straightforward. Now we have altitudes that are similar, or that fit the same ratio as the rest of our triangles. So one more time, I just want to say it again so you can hear it. Similar triangles have corresponding altitudes proportional to corresponding sides. Okay, we have one more that I want to talk about today, and it says if two triangles are similar, the lengths of the corresponding angle bisectors are proportional to the lengths of the corresponding sides. So we talked about altitudes. The same thing goes for angle bisectors. Now I noticed that on the diagram they had forgotten to annotate that these angles are the same. Okay, that's how you're going to know if it's an angle bisector or not, if both angles on the line going through the vertex are equal. Okay, now that doesn't guarantee anything about these side lengths. It doesn't say they're equal, nothing like that. It just guarantees that the angles themselves are the same. Okay, so if we're talking about a similarity statement, we can say that these angle bisectors, RT and LP, when you compare those, they have the same ratio, follow the same scale factor as LM to RS. All right, and once again, it's not the theorem of angle bisectors. There's no fancy name for it, so we're just going to have to use abbreviation for this one. It says similar triangles of corresponding angle bisectors, proportional to corresponding sides. So what you'll notice is, and we're going to do another theorem like this tomorrow, if you can just remember, similar triangles have corresponding, and then this is really the only word that changes. So once you have them down, you'll know what you're talking about, and all the theorems kind of go together the same way. But enough talking. I think we get the idea. If it's an angle bisector, that also qualifies to be part of my scale factor. So I could compare LP to RT, and I could also compare it to LM to RS. I could compare LK to RQ. I could compare KM to QS. All right, and so if I know that these are similar through angle or from whatever, and I know I have angle bisector, I can also put that ratio in with my similarity statement. So just make sure that, like I said, I think they forgot to annotate that these were equal angles. So it looks like angle A is being bisected because it has two equal angles, as well as angle F is being bisected. They have two equal angles. So I guess the first thing I need to do is I need to make sure that it's similar in this case. since I don't see a side, 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 or a side angle side, it doesn't tell me any of that information. I need to make sure that read the directions to make sure they are similar. In this case, it guarantees that triangle ABC is similar to FDG, so I'm good to go as far as my theorem about angle bisectors. Okay, so I know that the ratio of the angle bisectors is the same as the ratio of the corresponding sides of the similar triangles. So what I'm going to say is, in this case, x over 8 equals 15 over 12. So my proportion, 12x equals, let's see here, 15 times 4 is 60, so that must be 120. X equals 10. And so I've found the length here. X equals 10. All right. So, of course, in your homework, they're going to be a little more challenging than the simple example I gave you, but like I said, these theorems, there's no really abbreviation for them, so you just need to remember the statement. Similar triangles of corresponding, it could be altitudes proportional to corresponding sides, or angle bisectors proportional to corresponding sides. So those are the two we're doing today. We're going to do a couple more tomorrow. So we're going to practice these, and then we'll go from there. So that's it for today.